The concept of energy applies to the movement of cycling when the bicycle is being pedaled, as seen in the clip to the left. Muscular energy, being produced by the force of the legs pedaling the bicycle, is being transformed into mechanical energy. Kinetic energy is associated with motion of an object. An object with greater mass or velocity has greater energy. Factors should be considered include drag, rolling resistance, and grade of surface. Energy produced by top riders can generate about 300 to 400 watts of power, which is as much as 3 to 4 old-fashioned 100-watt lamps. Cyclists have utilized the rich source of kinetic energy by harvesting this energy during speedy and balanced maneuvers. It is important to minimize the increase in extramuscular activity while maximizing the efficiency of human movements. Studies have shown cyclists who utilize lateral oscillation of bicycle frame or weaving caused by the user's weight-shifting movements in order to increase the pedaling force in uphill riding or during quick speed-ups.
Total energy is a summation of both PE and KE. PE, or potential energy, is the stored energy of a position of an object. It equals mass times gravity times height. KE, or kinetic energy, is the energy of an object in motion. It equals 1/2 mass times velocity squared. As the figure shows, the cyclist at the top of the hill is sitting still and only has potential energy. As he begins riding down the hill, he loses potential energy and gains kinetic energy. When he reaches the bottom, he's used all his potential energy and now is only using kinetic energy.
Collision can be described as the total momentum of the system being equal to the sum of the mass times velocity of all colliding objects. Factors considered when discussing collision include mass of the bicycle and rider, mass of object forcing collision, velocity of all colliding objects, lower extremity, and rotary motion. Understanding collision will help cyclists prevent injuries in the future. Let's consider a collision that occurs between a bicycle and a car. Studies show the knee height of the cyclist relative to the hood leading edge affected the global kinematics of the head impact location against the car, a cyclist being hit on the side. The loading mode of the lower extremities was also dependent on the initial positions of the lower extremities relative to the car structures. In the foot up and front posture, the knee was loaded in a lateral shear direction by the hood leading edge, and as a result, the ACL ruptured. The bicycle frame and the struck side lower extremity interacted and could influence the loadings on lower extremities. The injury that occurs from a collision, such as a car versus a bicycle, will be determined by the angle the rider is hit and the location of the rider's lower extremity at the time of impact.
Torque is a measure of how much force is acting on an object, causing that object to rotate. In cycling, torque occurs every time force from the lower extremity is applied towards the pedals and the crank. The main factors that affect torque when cycling are the length of the crank, the direction of the pedal, and the anterior and posterior position of the foot on the pedal. When cycling, the passive leg is always raised by the propulsive forces of the active leg. A common error is pulling up on the pedal in the recovery phase. This creates a resistant torque and can lead to injury. Injury occurs when the thigh or the shank cannot rotate about the vertical axis, and it places a greater joint moment on the knee, which can lead to injury. In general, the highest torque levels are recorded at the lowest cadences with the greatest pedal crank lengths. When the crank reaches its greatest length due to the size of the cyclist and the bicycle, torque must be maximized by direction of pedal force. The downward phase requires the pedal to be pushed forward and down, while the upward phase requires force on the pedal to be backwards and up.
Power and work are two concepts that are very closely related. Work can be defined as the average force placed on an object over a distance. Work efficiency, a key term used in research on cycling biomechanics, is defined as a ratio of work done on the load and the metabolic cost of exercise. Power, on the other hand, is the amount of work performed over a given time. So if two cyclists put in the same amount of work, but one cyclist got there first, that cyclist had more power. The second place cyclist could improve his power by altering his pedal speed or cadence, increasing his cycle frequency, or changing his crank length. The biomechanics of uphill versus flat ground cycling differ, although research completed by Miller et al. Showed that a small incline only changed the positioning and not the work efficiency of the cyclist. It is thought that efficiency and other factors are affected with steeper inclines because there is a significant decrease in pedaling cadence. Interestingly, peak and minimum torque occur 5 degrees later in the crank cycle when going uphill. Within uphill cycling, you must also look at the biomechanical differences in seated versus standing cycling. Standing results in an increase in peak pedal force due to the removal of saddle support, which means more work is done using body weight instead of muscular force. Standing also changes the muscle activation, which can affect the amount of force a rider is able to use. When riding on flat ground, a rider mainly has to overcome wind resistance, which is typically easier than overcoming gravity with uphill cycling. On flat ground, a higher gear is used to be able to accelerate, while on hills, a lower gear is used to be able to climb as efficiently as possible.